Let's continue our study of the trends on the periodic table. We're going to look at 4 trends today in the notes. The first trend or pattern is the trend for atomic size, which will be referred to as atomic radius. On the notes, you will notice there's a rectangular box. This just simply represents our periodic table as we go from francium on the bottom of the alkali metal families all the way up to fluorine, the top of the halogen family. So I want to just point out to you that the noble gases are not included on the trends that we're talking about. You always want to think about your noble gases separately as they would pertain to each specific trend. But the trend for atomic size is as you go up a family or group and across from left to right on the periodic table, the size of your atoms tend to decrease. So your larger atoms are going to be towards francium. Keep in mind that the period numbers tell you the number of energy levels. So francium in the 7th period would have 7 rings around the nucleus if you were to draw the Bohr model, whereas hydrogen up here at the top would have only 1 ring. So obviously as you go up a family, you get fewer and fewer energy levels. You can think of it that way. So the size decreases as you go up and decreases as you go across towards fluorine. So it's kind of like a snowman. When you build a snowman, your large snowballs go on bottom, and as you go up, they decrease in size. And then if you were to kick the snowman over, so just pretend you kicked him over, and you notice that the small part is going to be over towards fluorine. That's one way that maybe can help you remember. Now, while we're talking about size of our atoms, I also want to talk about size of our ions. We talked about cations and anions in the last unit. Remember, cations form when an atom loses electrons. We learned that our metals form cations. So when an atom loses electrons, and it will be a metal atom, it would be then forming a cation. What happens is your cation is always going to be smaller than their neutral atom. Think of it kind of like if you go on a diet and you lose weight, you would get smaller in size. So since cations are losing particles, so they're losing their valence electrons, they're going to get smaller than they were when they were an atom. So for example, the sodium ion is going to be smaller than the sodium atom. Here we have a Bohr model of the sodium atom. Notice it has this 1 valence electron. When sodium, the atom, loses this valence electron, it then becomes the sodium ion. This will be your sodium with a +1 charge. Notice it no longer has its 3rd energy level. So you see what's left over is the 8 electrons in the 2nd energy level, which now it has an electron configuration of a noble gas. So it would look sort of like neon. Now, on the flip side of that, if you have an anion, we learned that anions form when an atom gains electrons. We also learned that it's our nonmetals that form anions. The anions are going to be larger than their neutral atom because they gained electrons. So again, it's akin to gaining weight. You get larger. If I give you oxygen, the atom, versus the oxide ion when he has a -2 charge, and I were to ask you to compare the size, you would tell me that oxygen, the atom, is smaller than the oxide ion because here the atom of oxygen has 6 valence electrons, but for the ion, notice he gained 2 extra electrons here. So it's again like gaining weight. It gets larger. Now our next trend is called ionization energy. And so I will abbreviate this oftentimes with an I and an E for short. So if you see that, I'm talking about ionization energy. Ionization energy is the energy needed to remove an electron from a gaseous atom. So how much energy it would take to take the electron off of the valence shell of an atom. Again, we're going from francium to fluorine. As you go up a family and across the periodic table, this trend increases. It's very hard to remove an electron from fluorine. Remember, fluorine has 7 valence electrons because he's in group 7A. He only needs one more, so he's not going to easily give up any electrons. In fact, he's going to hold them very tightly. Francium, however, wants to lose his 1 valence electron that he has, so he will be very easy to take an electron off of. So as you go up, it increases, and as you go across, the ionization energy also increases. So francium has the lowest ionization energy between these two atoms we're referring to, francium and fluorine. It would be the easiest to remove the valence electron from because he holds his electron very loosely. On the other hand, fluorine has the highest ionization energy. It takes the most energy to remove an electron from him because he holds his electron very tightly and shields it. The next trend is called electronegativity, and it has this symbol. It's a Greek letter chi. When you write it out, it looks kind of like a cursive X or maybe 2 C's back to back. But it's a Greek letter chi. That's our symbol for electronegativity. This is the ability of an atom to attract electrons to itself in a compound. So it's when an atom, let's say an atom X, is trying to bond with another atom Y. They're vying for the electrons. They're pulling, if you will, on the electrons, kind of like a tug of war. So one of the atoms typically is going to pull harder because it's going to want the electrons more. So as you go up and across the periodic table, this trend tends to increase, just like ionization energy. Fluorine's electronegativity is 4.0. That's the highest this scale goes. And francium's is only 0.7. So francium does not pull very hard on electrons at all, whereas fluorine is going to pull very hard. He wants electrons so that he can fill his valence shell. Francium has the lowest electronegativity of our trend that we're looking at here, is a 0.7. Fluorine has the highest of 4.0. Now keep in mind the noble gases, which would be found over here on the periodic table, they have 0 electronegativity. So if you were to be asked about a noble gas, keep in mind they don't participate in bonding. They already are stable. They don't need any more electrons in their valence shell to stabilize them. So their electronegativity is technically the lowest of any group of elements. Our final trend is called electron affinity. Electron affinity is the energy needed to add an electron to an atom. So it's exactly the opposite from ionization energy. We abbreviate this with an EA for short. The trend for electron affinity as you go up and across is it decreases, just like atomic radius. So as you go up and across from francium to fluorine, electron affinity decreases. Francium is the hardest to add electrons to. It's going to take the most energy. If you try to add an electron to francium, he will not take it. Remember, he wants to get rid of his valence electron as it is, so he's not going to take any electrons. This has the most endothermic energy value. Fluorine, on the other hand, is the easiest to add an electron to. It takes the least amount of energy. He would be very easy to add an electron to. It's the most exothermic energy value. Now, when you think about electron affinity or ionization energy with the noble gases, keep in mind they are the most difficult to add an electron to or to take one away from. So with the noble gases, they have very high electron affinities as well as ionization energies. All right, so that's our lesson on the 4 trends: size, electron affinity, ionization energy, and electronegativity. Hopefully that will help you with your homework.